Hello everyone, I am Vishwakarma from Ramdeobaba University. My roll number is 6 and on my teacher assessment I have been given the topic quantum gates and De Morgan's law. So specifically we are going to cover essential single qubit gate like Pauli exclusion gate, Hadamard, and in multi-qubit gate we are going to cover CNOT gate, Toffoli gate, and finally we are going to look at De Morgan's law and how crucial it is for quantum computers. So let us begin. Before we see the gates, we have to understand the rules of the game. So on your left, you can see the classical gates. You know these gates are AND or XOR, etc. They operate on bits strictly 0 and 1, but they have a flaw. They are mostly irreversible. Think about it as AND gate. If the output is 0, can you guess what were the inputs? No, right? It could have been 0 0, 0 1, or 1 0. You have lost information. But as you can see on your right, there is quantum gates. It operates on the qubit, or we can say superposition of 0 and 1. The golden rule here is that quantum gates must be unitary, which implies they must be irreversible. To run a quantum circuit backwards, you must be able to retrieve your original input. This requirement changes how we design everything. We can't just erase a qubit, we have to transform it. Okay, so let's begin the Pauli X gate or quantum knot. If you are coming from a computer science background, just call it a NOT gate. It is a quantum equivalent of backflip. It takes a state of zero and turns into a one, or vice versa. Mathematically, we represent gate as matrix. Look at the matrix in the middle of your uh, sorry. Okay. Mathematically, we represent gate as matrix. Look at the middle of the screen. If you multiply the vector from 0, 1, 0 by this matrix, the row swaps and you get 0, 1. On your right, you can see a sphere. This is how we visualize a qubit. The poly x gate rotates and the state vector 180 degrees around the x-axis. It literally flips the qubit upside down. You can see the operation here. Okay, so let's start poly y and poly z gates. On your right, you can see poly z gate, and it is fascinating. It flips the face. Notice the matrix. It has a negative 1 in the middle right. This means if your qubit is in state 1, it adds negative 1 sign. Or we can say add a phase of 180 degrees. If a qubit is 0, it does nothing. Why does this matter? In quantum computers, in classical computers, minus 1 is just an error. But in quantum computers, the negative sign is used to create the interference pattern, cancelling out the wrong answer in algorithm. While in poly, Y gate is a combination. It performs both bit flips and phase flips simultaneously, rotating around the y-axis. It, it introduces the imaginary unit I, or we can say iota, which is essentially for complex quantum dynamics. Okay, let's start Hadamard gate. If there is one gate you must memorize, it is this one. The Hadamard gate is denoted by H. This is where the quantum magic happens. If the poly X gate just the flip a bit, that's classical. But Hadamard gate creates a superposition, which is in between 0 and 1. If I start with 0 and add and apply Hadamard gate in it, it will not give me 1. It will give me a probabilistic answer, which is between 0 and 1, which is simultaneously both 0 and 1. We call it a plus state. As you can see, it is denoted here. Look at the matrix. It has ones everywhere except the bottom right corner. This gate is used at the start of almost every quantum algorithm because it allows the computer to process all the possible inputs at the same time. It opens the door to quantum parallelism. Okay, now let's start with CNOT gate, or it is also known as control NOT gate. What happens here is if in control unit we have 0, it will not change the answer. Like if we have 0 in the control unit and 0 in the target unit, the output will be 0. And, or if we have 0 in the control unit and 1 in the target unit, the output will be 1. It will not change the outcome. But if in control unit we have 1 and if in target unit if we put 0, the output will be 0. Or we can say it just reverses. If it is 1, then it will change to 0, and if it is 0, it will change to 1. You can see the circuit symbol here, and what I've said is written over here. Okay, let's start with Toffoli gate. It is just a CNOT gate with an extension. It is also called as CC0 gate or control NOT gate. If C0 is a 2-qubit, the Toffoli is a 3-qubit evolution. It is also called as CC0, as I've already said here. Target flips if only both control units are 1. Otherwise, it will give the answer, or we can say it just copies the output. It copies the input which you have given. Why is this gate famous? Because it is a universal for classical logic. Remember, I said quantum gates must be reversible. Well, a standard NAND gate is irreversible, but Toffoli gate is. This means any programmer, as a programmer, you can run on in any laptop. You can technically run on a quantum computer using arrangement of Toffoli gate. It is a bridge between classical Boolean logic and quantum circuits. Okay, let's start with Fredkin gate. Similarly to the Toffoli, is it is also known it is similar to the Toffoli gate or control swap. The logic is simple. If the control bit is 1, two target bits trade places. If the control is 0, this stay put. This is a this is a conservative gate. What I mean by that is if you put two ones and a 0, you get two ones and a 0. The Hamming weight number of ones never changes. The property makes the Franklin gate very useful in error gate correction codes and specifically in physical implementation of quantum computers where energy conservation is the key. Okay, let's start De Morgan's law. In classical logic, you might remember this from a discrete math. It states that the negotiation of the conjunction is a discussion of the negotiation. Or in layman language or in plain English, we can say you can build an OR gate using AND and NOT gate. The formula is on the screen. A NAND B is equivalent to NOT A or NOT B. But why are we studying this in the quantum lecture? Because if you have to use OR gate, it is not directly given in the quantum computers. You have to make it using AND gate and NOT gate in it. So this is why this law is very useful in this quantum computing lecture. The formula is given over here, and you can see, as I've said, the NOT gate is not directly OR gate is not directly in the quantum computers. We have to make it, and the diagram is shown over here. Okay, the application or quantum OR gate. Let us trace how exactly a quantum OR gate using De Morgan's law. Imagine this circuit in your head. We want to calculate A or B. Step 1. The setup. We take our inputs qubit A and qubit B. We apply Pauli X gate to both. Now we have not A and not B. Step 2. The operation. We feed these inverted qubits into Toffoli gate. The Toffoli gate and the operation. So we have not A and then not B. The result. We apply one final we apply one final Pauli X to the result. According to the De Morgan's law, the negating that AND operation gives us the logical OR of the input. This is perfect example of how we combine the single qubit gates Pauli X and multi qubits like Toffoli to perform logical oh, arithmetic. To wrap up, here is what you need to know to take away today. Poly X are the rotation X, which is just a NOT gate. Hadamard is a superposition gate essentially for parallel processing. CNOT and Toffoli allow qubit to interact. Toffoli allows us to perform any classical computing reversibly. While De Morgan's law isn't just in a textbook rule, it is a blueprint of constructing logical gates like OR, given that we are already constrained to reversible operations. Okay, thank you for your attention.